Now that we know what a linear equation is, let's look at what a linear system is. So a linear system is a collection of linear equations that have to hold all at the same time in order to obtain a solution. For instance, I could have the general linear system here. A1x plus b1y equals to c1. So here a, b, c, they stand for constants, and my variables are x and y, so we're currently in R2. And I've got another equation, a2x plus b2y equals c2. In some way, when I want to solve this, okay, I need to find values for x and y that will satisfy both equations. Sometimes there aren't any such values, in which case we'll say there are no solutions. Sometimes there is a solution and it's unique, so we'll say there's one solution. Maybe sometimes there are two solutions, 3, 4, 5, and we'll see that there's something kind of surprising about all that. But right now, let's look at an example. So I wrote down the linear system 2x plus y equals 4 and x minus y equals minus 1. So you have probably done this in Sec 4, solving a system like that. Therefore, what I'm about to do will probably not be very surprising. It's kind of like a little review. I could obtain the solution graphically if I can. Okay. How do I do that? Well, I could draw the first line, 2x plus y equals 4. All I need is 2 points in order to draw that line. Therefore, I'm going to maybe set y to 0 and solve for x. If I replace y by 0, 2x is going to be 4, so x is 2. So maybe here, 2. And if I replace x by 0, y is 4. So this is the solution set in some way of the first equation. So all points on this line satisfy the first equation. So I have the solution set of the first equation. And now I'm going to look at the second equation. X minus y equals to minus 1. Again, I can replace y by 0 and solve for x. I get x is negative 1. And if I replace x by 0, y is plus 1. Therefore, this is the line. So what I see, so maybe let's rewrite down what I had said before. This is a solution set. It's a set, right? It's a collection. Think of a line as a collection of points. When you take the union of all these points, you get a set. And all the points in that set are solutions of the equation. Solution set of first equation. And here you've got this other line. That's a collection of points too, right? It's the solution set of the second equation. And essentially what we're looking for is a point that belongs to both sets. And we can see here that there's a unique point. Okay, there's a unique solution here. So the solution set, so what we're looking for when we're solving that linear system, that solution set will consist of only one element, 1 point. So maybe a Sec 4 method for solving this system could consist in, I don't know, you could multiply the second equation by 2 throughout. So I multiply everything by 2. So 2x minus 2y equals minus 2 is just the same as x minus y equals minus 1, but written differently. But the advantage is now I have 2x and 2x here. I could cancel them by subtracting. I could subtract the second equation from the first equation. If I do this, over here I get 0, like 2x minus 2x is 0. Y minus 2y, that's 3y. And 4 minus 2, that's 6. So 3y is 6. And that implies, see the arrow for implies, that implies that y is 2. So I know that in my solution, well, my unique solution has a y coordinate of 2. To get the x coordinate, all I need to do is use one of the two equations in my system and solve for x by replacing y by 2. So if I take maybe the second y, and I know that x minus y, but y is 2, that's minus 1. So that's going to imply that x is 2 minus 1, so x is 1. So the x coordinate actually is 1. So 1, 2 is a solution, is the solution of my linear system. And you can verify that this is correct, right? You can replace x by 1, y by 2. 2 times 1 plus 2, that's 4. 1 minus 2, that's minus 1. So it's correct. It's at least a solution. And with the steps below, we've established that it's the unique solution. We've also established that with the graph. So the solution set, maybe let's write it down. The solution set, or the solution here, is xy is equal to 1, 2. Here we go. Okay, so when I write this, it means x is 1, y is 2. Okay, that's another way of writing it down. Let's look in general. What are the possible situations that I could have? I could have what? I could have the situation I just had previously. Two lines that intersect somewhere in a unique point. Okay, so that's my previous example. Okay, in this case, there's only one solution to the linear system. When there is at least a solution, we say it's a consistent linear system. Consistent means there's at least a solution. It's consistent. So consistent, the linear, no, messed up here. Consistent linear system, and consistent means at least one solution. That's the definition of that word in this context. What's another possible situation? I could have like two parallel lines like that, right? They don't intersect. How many solutions would I have? Infinitely many? 0? Well, let's take a look. Those are points that are part of the first solution set. Those are points that are part of the second solution set. I have a solution set of the second equation, right? So in blue, I've got points in the solution set of the first equation. In green, points are part of the solution set of the second equation. The solution set of the system would be a point that belongs to both solution set at the same time. And here, clearly, there isn't such a point. So I have 0 solution here. No solution, or no solution. We say the system is inconsistent. Inconsistent linear system. Can you find an example of a system like that? Let's say the first equation is this. Could you find like a second equation that would be such that I would have no solutions? Well, think about the first equation, right? It'd have like a normal vector that's 2, 1. So for the second equation, you also want to have a normal vector that's at least proportional, right? Maybe this is n1 and 2. You want something that's proportional to n1 so that the normal vectors are parallel and therefore the lines are parallel. So that means you want to have here, for the coefficients of x and y, multiples of 2 and 1. So maybe I could add like 4 and 2. Okay. And you don't want these lines to be overlapping. You don't want to be on top of each other. You want them to be parallel but distinct. So you don't want, so here you see it's as if I've multiplied these coefficients here by 2. You don't want to multiply that one by 2, because if you do that, you'll have the exact same line. So I'm just going to keep it at 4. And this way it's a completely different line, but it's parallel to the previous one. And finally, there's the situation where you've got two equations where the lines actually overlap. It's the same line. So for example, if now I multiply everything by 2, it's the exact same equation, right? I've got a system, but in fact this is equivalent to just having the first one, because the second one is just a repeat of the first one. Therefore here, how many solutions do I have? Well, let's take a look, right? I've got points on, right? If I look at my first equation, if I look at points that are part of the solution set of the first equation, they're on that line. If I look at the second equation, it's actually the same equation, so the points are also on that line. So do I have points that are both parts of the first and the second solution set? Yes, there all these points are. So here I've got infinitely many solutions. Sometimes I'll just write this for infinitely many solutions. And I've got, of course, a consistent linear system because there's at least one solution. So those are, you'll agree, those are the three possible cases when I have two lines. If I've got three lines, like if I would have like a third equation, I could of course have something, you know, I could have different things. I could have like two parallel lines with one that intersects them. In this case, do you think there are two solutions? 0, 1? Well, again, if you think of the points that are part of the solution set of each line, right? There are these points. After that, maybe the second solution set would be those that belong to this line. And for the third equation, I have points that are part of this line. Actually, try to find a point that's both red, green, and blue. You won't find one. So here, you see there would be no solutions here. Okay. To have one solution, I'd have to have something that where my lines actually all intersect in one point. So this would be one solution. I could have two overlapping, one intersecting. Oh, in this case, one solution. If all three lines are exactly the same, oh, then I have infinitely many again. Okay, but in all cases, basically, you see I have either 1, 0, or infinitely many. And this is a theorem we are going to prove eventually. But I'll write it down here. So theorem. So linear systems with two variables. So in R2, I have either 0, 1, or infinitely many solutions. Now you'll ask me, like, how do I describe a solution set? Okay, how would I describe it if it's not through the use of a graph? So actually, let's describe the solution set of one equation. Okay, let's start with that. So let's say we look at actually the solution set where it's the same equation repeated. So the solution set, you know, here is the solution set of that equation, 2x plus y equals 4. So let's look at that equation and its solution set. So the solution set of 2x plus y equals 4. Well, what could I do? I could, you know, try to come up with all the points, but there are infinitely many. That doesn't sound like it's a good idea. But let's say I start with that. If x is 0, y is 4. Okay, so that's a point. If x is 1, y is 2. Okay, that's another point. But I forgot like kind of a lot of points between 0 and 1, right? There's also a half, right, that I forgot. So 2 times a half is 1. So y wouldn't be 3. But there also forgot, I don't know, 0.0123, okay, and I would have to figure out the y. So that's not going to work, right? I can't enumerate all the points. There are infinitely many of them. All right, so that's a no-go like that. I'm not going to use that technique here. That's not going to work. Well, okay. What I could do is I could write the equation of the line in vector form. Okay, you'll see that when I do this, it's going to give me a way to actually get efficiently all the solutions. So how do I do that again? Well, I need a point to write it in vector form. Well, what do I need, right? I need, if this is the line, I need a point and I need a vector that's parallel to the line. So what's a point on this line? Well, I've got one, right? 0, 4. Here we go. What's a vector that's parallel to the line? Maybe it's easier to come up with the normal vector. N, which is what? N is 2, 1. And maybe a parallel vector. That's easy. I just switch the coordinates and hit one with a negative sign maybe. Here we go, like that. This way I've got, right, I've got N, and to get V, which is perpendicular to N, you do that, right? You switch the coordinates and you hit one with a negative sign. And this way I can write down what the equation of the line is in vector form. It's going to be 0, 4, well, xy 0, 4, plus some multiple, so t times maybe 1 minus 2, where t is a real number. I could also write it like that, 0, 4 plus t 1 minus 2. I could regroup everything together. That's also possible, right? 0, 4, t minus 2t, and finally put everything together. So this is t, comma, 4 minus 2t. So this is how I could write it down as well. Okay, it's also still understood that t is some real number. So by writing it this way, you see, I could, it sort of lists all the possible solutions, because give me your, especially with this, right? Because give me a value of t, I can generate a specific point. Give me another value, I can generate another point. So you see all the points I had up there, I can generate them, right? If I set t equals to 1, then I get 1, 2, which was the point I got there. If I set t equals to 0, I get 0, 4, which was this point over here. And I can list them all. So in some way, by writing this, I'm listing all the points, but actually in a very efficient way. So the reader can just generate all the points that he wants by assigning all the values of t, all the real values to t. And by the way, you can always check that this is correct. How do you check that your answer is correct? You substitute, okay, in the above equation, right? So 2x plus y, well, if x is t and y is 4 minus 2t, if it satisfies the equation, it should be getting 4 in the end. So I get 2t plus 4 minus 2t. Yes, it's 4. Here we go. It works. Here's another technique. Here's another technique, and this is the way we're going to actually solve these equations in the future. You assign an arbitrary value t to one of the variables. So t is called a parameter here. So it's like saying, okay, so t could take on any real value. It's like saying I'm going to assign to y the value of 1 and solve for x. I'm going to assign a value of 2 to x and solve for y. Okay, so I can do that and get a point. So I'm going to do this, but here I'm going to keep t arbitrary. Okay, so I'm going to say, maybe say I'm going to assign I'm going to assign t to x, okay? And after that, and we'll replace x by t and solve for y. So if I do this, I get 2t plus y equals 4. So y is 4 minus 2t. And with this, I can come up with my solution set. xy is going to be t, 4 minus 2t. And with this, and saying, assuming r is some real number. And with this, I once again have a list of all possible points. So assign a value to t, for example, t is 0, then y is 4. Assign a value of t to 1 to t, then x is 1, and and y is 2, and so on, and you've got all the possible points. If I compare my two solution set, they look, they're actually identical. You see, t 4 minus 2t was what I had obtained previously. I get the exact same thing here, so you can, so this is the exact same list of points, but obtained differently.